All right, differentiation and integration of vector valued functions. So, I'm going to be a little bit lazy with my definition here. Right, so again, think about a vector valued function, right? It's basically the same thing as a parametric function. It's just you're thinking of some point moving through space, right? And the t is just controlling where it goes. And so when we talk about the derivative, back in Calc 1, what was the derivative measuring? Why did we first introduce the derivatives? To compute slopes of tangent lines, right? So you had a curve like this, and we said, okay, well, we start at this point A, right, and we take the next point and we get an approximate tangent or slope for a tangent line, and then we take the limit as we go here, and that should give us the slope of that tangent line, right? So now, if you just think of some vector moving through space like this, if you get here and you compute the derivative, it should still correspond with the tangent, but now it's going to be a vector that sort of points in the direction of where we're moving. Does that make sense? So it should do that same thing. It should be a tangent vector that's kind of pointing in the right direction. So let's do this. So the definition is just the limit as h goes to 0 of r of t plus h minus r of t over h, right? That's the same definition that you had for derivatives back whenever. But let me just point out that, again, we assume our r is a vector valued function, right, that has the form f, g, h. Those are your components. And so if you do this, break this up, this is just, right, f of t plus h. I'm just going to do two vectors here, g of t plus h. Oh, I'm using h. That's good. I'll just do the 2D version, right, but the 3D version, exact same thing happens. And then this would be f of t, and then g of t. So if you subtract vectors, how do we do that? We do it component-wise, right? And so, okay.
Like terms?
Well, not even like terms, right? It's
Each one.
3, 2, minus 5, 1, right? You do 3 minus 5, right?
Yeah.
And so that's all I'm saying is, so I guess it's sort of like terms if you think of the f's. But this should just become, and actually I'm going to just do it all in one thing. Dividing by h is the same as multiplying by 1 over h, right? That's just a constant. And so when you do this, you'll just do f of t plus h minus f of t divided by h, right? And then in the g component, you'll do the exact same thing. Divided by h. And then we've already talked about how you compute limits, right? The limit slides into each piece. And those are precisely the derivatives of f and g. That makes sense? So computing the derivative of a vector valued function just comes down to computing the derivatives of those components. I don't have to do anything different. So let's just do an example here. And this, right, was for a function or a vector valued function in R2, but in R cubed it's the same thing. So example, find r prime of t Actually, let's make this slightly more interesting. Not much more interesting, but a little bit. cosine down on the bottom. So, this looks like a new thing, right? The derivative of a vector valued function, but it's just turns into 3 derivative problems, right? So it's one vector problem turns into 3 problems you would have done back in Calc 1. So you just do the derivative at each piece. The last one's the easy one. What is it? 5t to the 4th, right? Good? All right. How about the middle one?
3 cosine. 3 cosine.
Actually, first, so it's sine this. It's been a while since you've done some basic derivatives, probably. So let's just take our time, right? So it's something to the 3rd power. So how do we deal with that? 3 sine squared, right? T, and then times the derivative of the sine, right? The chain rule, so it kicks it up. So there's okay. All right, and then the first one requires what? Quotient rule, right? So what's the quotient rule? Derivative at the top. 1 times bottom minus top times derivative of the bottom, which is negative sign, so we end up with plus sign, and then all over cosine squared. Okay? Okay. So again, if you feel rusty at all with your derivatives, you know, you might want to take a minute and just go back. And practice. And so let me just say, no, I won't bother proving anything, but r prime of t points in the direction of the tangent line. Okay, and so now if we're talking about functions of 3 variables, right, you're talking about a tangent line in 3-dimensional space, and so we have to compute our equation of lines using the stuff we did in the last section, right, when we talked about lines again. So we'll do a 2D version and then we'll come back. And we'll come back and do a 3D whatever. But let's do this. I'll break this up into a couple pieces. So let R be this. So what I want to first do, break this up into a couple pieces. Sketch R and plot the point for t equals pi over 6. Okay, so I think we did a little bit of plotting these basic things, right? Remember the idea? Here's x, here's y. So what equation do those satisfy?
X squared plus y squared is 1.
X squared plus y squared is 1, so you should be on the circle of radius 1. So sketch it, see if you can remember how to figure out which direction we go around that circle. And in fact, I say find the point for t equals pi over 6, but give me the point when t is 0, right? I mean, you don't have to make it explicit, but just know where t is 0, and then where do you move from there? Do you go up, do you go down, do you go left, right? So sketch that, and then if you're done with that, find r prime of t. Again, shouldn't take too much time. And sketch r prime of pi over 6, starting at, I'll write it this way. So sketch the derivative vector, right? So the derivative vector, but then make its base start at the same point that you're plotted in the first piece. So try those for a minute. before. This should be a circle of radius 1. You don't have to draw on the dotted one if you don't want to. But again, all that we know right from the start is that r x squared plus y squared is 1. So you know you're on that circle. I didn't give bounds for t, so that means you should assume all t. But let's start with t equal to 0 and then move on from there. So when t is 0, where are we at? 1, 0. So we're here. And then as t grows, where do we go? Up or down? Up. Why? You're right. But why?
The numbers just.
Cosine of 1.
Right. So you could go check some values, but the thing I like to think of is the sign, right? The sign goes up, and so that's your y values. So if you're starting there and your y values go up, you have to move up. So we're going to move in this direction around our circle. All right. Where is t equals pi over 6? So let me just say r of pi over 6. So cosine of pi over 6, sine of pi over 6. So what point is that?
Square of 3 over 2,
Root 3 over 2, and then
1/2.
yeah. Good. Okay. Now, that's not a circle that I drew, right? I'm trying to draw a circle, but it's very ovally. So your point's not going to correspond perfectly with it, but hopefully you get that. The point is it's over here somewhere, right? It's further in the x direction than the y direction, roughly at that 30-degree angle. So the point kind of corresponds to that. Okay? All right. Now, what's the derivative here? This should be easy.
Negative sign.
Negative sine of t and
Sin t.
positive cosine of t. Good. Does that make sense? So now evaluate this at pi over 6. And so we just figured out sine and cosine of pi over 6. So what are we going to get? Negative 1/2 and then positive 3/2. Does that make sense? And so I said come over here and sketch that vector. So x was negative 1/2. This is root 3 over 2. So again, don't worry about exactly where it is, but the point is your x values are going to go a little negative, right? And your y values are going to be square root of 3 over 2. That vector is going to look like this. Right? So you're moving around the circle this way, and your tangent vector, when you get there, should just be the spot you'll stop. Right? You think of spinning or something on a rope. When you let go, right, it'll fire off in the direction that it was at. That's exactly what's happening here. Right? You spin something around, and if you stop right there, that was the direction you were going without any other force acting on it to pull it onto the line and continue on. Does that make sense? And so, much easier to draw in 2 dimensions than in 3, so I'm not going to even bother trying to see what it looks like in 3 dimensions, but that's the idea, right? Even if you got something moving like this, and you stop at some point, it'll continue off in whatever that trajectory is. Okay. So, let's define this. So in the next section, we're going to talk about curvature. And so when you talk about something curving, so you really want to think about how does that direction vector change, right? So if you curve, your direction vector is going to be moving around. If you're in a straight line, your r prime will just stay straight, right? And so when you talk about curvature, you worry about how that thing turns. But if I replace this with 5t and 6t, okay, let's not do the whole problem again. What's the difference between the graph of cosine of t, sine of t, and the graph, oh, not 5 and 6, 5 and 5. And cosine of 5t, sine of 5t.
The sign.
They still satisfy x squared plus y squared is 1, right? So what's that 5 do? You're still on this curve. What's the 5? What sort of property does it have? Or maybe just, let's do it over here with 2. So suppose you get this vector, cosine of 2t, sine of 2t. Right, so back on this graph, this was when t was 0. We got up here when t was pi over 2, right? So think about this one now. It still satisfies that equation. It's still going to go around like this. You're going to be here when t is 0, right? Where are you at? What's r of pi over 2 for this guy? Well, it's cosine of pi, right? And it's sine of pi. Oops. So what's cosine of pi? -1. Sine of pi is 0, right? So you got to here in the same amount of time. Does that make sense? So you started here, and you zipped over to here. And so if you think about what the tangent vector is going to look like at a spot compared to that tangent vector, what do you think? You're moving around the same path, but you're going twice as fast, right? And so if you think about that same idea of spinning something over your head, I don't know what you spin over your head, sock full of quarters, something like that. We used to play this game with my cousins. I'd take a sock and I'd stuff it with other socks. We called it, I don't know, some stupid name. But then you just beat each other with the socks, and it's awesome. You could wrap them around people's feet and knock them down. But anyways, so if you think about spinning something like that, right? If you let go, it's going to fly off in this direction. If you're going really slow and you let go, it'll fly off in that direction. If you're going really fast and you let go at the same time, it's going to go in the same direction, but it's going to be going a lot faster, right? And so if you find the tangent line here, it's going to be the same direction, but it's going to be like twice as long. Does that make sense? And so, is this circle curvier than that circle? No, they're exactly the same circle, right? And so when we measure curvature, we don't care how fast you're moving along or how long these tangent lines are. We just care about the direction and how that direction is changing. So, that's a long way to make this definition. So, definition. So, the unit tangent vector is, okay, so we'll denote it by capital T of t. This is all assuming you have some r of t in mind. And it's just the derivative vector divided by the magnitude of the derivative. Right? And so the point is that brings, no matter how you have your curve situated, it brings everything back to the same position, right? Where we just want a curve, a tangent vector of length 1. So we just scale our derivative to make it of length 1. Okay? And so in this section, we're just going to compute some unit tangent vectors, and then we'll do more with it next time. But I wanted to at least tell you why those matter. So let's do an example here. Just an easy one. Find the unit tangent vector for r of t for t cosine of 3t sine of 3t. And let's just do it at a specific point at what's next? Pi over 6. Okay. So take your derivative, plug in pi over 6, and then just make a unit vector in that same direction. That's all you're doing. Okay, so let's just do this. Derivative is what? 4. -3 sine of 3t, right? And then 3 cosine of 3t. Everyone good with that? Plug in pi over 6. R prime pi over 6. And I'll point out, right, you could compute the unit tangent vector with that mess, right? Do the square root of that. Maybe we'll even do that with this one. Let's just do that. Because this one's not too bad. So the unit tangent vector is r prime over the magnitude of r prime. So for this example, you could have just plugged in pi over 6 and then found the magnitude of it and divided by that, right? So that would have been fine, but it's also, this one's reasonable to do the whole thing at once. So your derivative is this 4, right, negative 3, which one was it, sine? 3t and then 3 cosine. Divided by the magnitude of that, and so in this case, what is that? 16 plus 9 sine squared, right, plus, it's going to be just plus 9, because then you get 9 cosine squared as well, right? Does that make sense? So you end up with just 5 then, right? Sine squared plus cosine squared is 1, so you get 16 plus 9, so 25, and the square root of it. So you're So your unit tangent vector just looks like this for every single t. That makes sense? Now, let me just point out that once you do this magnitude, this could get really ugly, right? In this case, sine squared plus cosine squared was 1, and so everything became nice and simple to work with. But in general, this is going to be a disaster down here and be really ugly to try to deal with. And so, you know, we just have to work around it. But again, back to the one we were asking, I said find it at pi over 6. And like I said, you can either do what we did here and then plug in pi over 6, or you could have plugged pi over 6 in here and here. And so anyways, we get 4/5 negative. Well, let's just do this in our heads. When we plug in pi over 6, what are we going to really do? We're going to evaluate sine at
3 pi over 6.
3 pi over 6, which is pi over 2, right? What's sine of pi over 2? 1. So this will be negative 3/5, and then cosine of pi over 2, which is 0. So there's your vector. Does that make sense? Okay. All right. And without actually showing the details, what did this R look like? So this R was 4t cosine of 3t sine of 3t, right? So it satisfies y squared plus z squared equals 1, right? So that means your y and z values stay on a circle of radius 1, and then your x values just come out, right? So if you plug 0 into that guy, you get x is 0, y is 1, right? And z is 0. So you start at this point here, 1, 0, 0 over here, and then you're going to spiral out of the board, right, towards us. And so it'll look something like, again, don't worry about any great details, but it's going to look something like that, right? You're going to keep spiraling your way around. And so it's just going to keep spinning out. And so when I see that my tangent line, my tangent vector has this form, negative 4/5, negative 3/5, 0. What's that 0 in the z direction telling you? So my rate of change, I don't change in the z direction. So is there any guess where we might be on this curve? Here, here, side, side, bottom.
The bottom.
Bottom or top, actually, right? Because all you know is that your derivative is 0 in the z direction, and so you should be flat. So wherever you were, if you think of flying around this circle and you get thrown off of it at some point, right, in the direction you're going, your z values won't change when you're at the top of this, or if you're at the bottom of this, and then you could check to figure out which one you were at there. Does that idea make sense? Okay. Let's see. What's next? Okay. All right, so this is another definition that we're going to be a little bit lazy with. And I'll just state it. So R of t is smooth on I if R prime of t is continuous on I and the derivative is never 0. Okay? So, do you remember back in calculus, Calc 1, we said a function was smooth. Do you remember what that condition was there? What made a function smooth? It's not really formally listed in the book, so whoever taught you it may not have even mentioned it. But smoothness essentially in that context means that you have derivatives of every order, but it was kind of, we also just used it for derivative back then. We said a function was smooth if its derivative existed. And so when we talked about drawing a function, a curve that was continuous, we said you could draw it without lifting your pencil, right? It was differentiable if you could draw it without doing what? So let me draw a couple examples. You tell me which ones do not have a derivative, right? So that's okay, right? That's bad. Something like that's bad as well. Does that make sense? So what did I have to do? I stopped, right? My chalk had to stop in order to make that sharp corner, right? And so these aren't smooth. It means their derivatives fail to exist. And so that's essentially what this definition is, right? It's saying your derivative is nice, it's continuous, and its derivative isn't 0 because being 0 means you stopped for a second, right? And so then you could move in any direction once you stop. And so essentially, it's the same idea of smoothness here. This is one of those things where as we move ahead, we're going to get theorems, and the theorems are almost always going to say, suppose you have a smooth vector valued function, right? And then you go on from there. And it only works with smooth functions. It's really hard to come up with a non-smooth function. If you just create something with functions that you're used to using, it's smooth everywhere in the domain of those functions, right? Because you know functions can be differentiated. So this is more of a technical definition that has to be in sort of sitting behind the scenes, but we really very seldom have to think about it. All right, so properties of the derivative here, I'll just write it like this. Okay, so if we have a vector valued function u, and we multiply it by a constant, right? That's the same thing as just doing the constant times u. These are all things that hopefully you buy. If you have two vector valued functions, u and v, so here again I'm going to start leaving off the u of t. These are not just vectors, they're vector valued functions, every vector I write up here. So the derivative of u plus v should be the derivative of u plus the derivative of v, right? Just like you were used to with functions. So that's all this is saying. You can take the derivative of u and then add or subtract it to the derivative of v. Okay. Let's do this. We actually have two different, well actually 3 different product rules, I guess. And they're basically the same as what you think. This time I'm going to write in the f, or the t's just to be clear. Okay. So if I have a function f just an ordinary function, and I have a vector valued function u, I can talk about what it means to multiply that function by the u, right? This is just like if I had t squared times a vector valued function, well, I just multiply the t squared into each component. And if I want to take the derivative of that, well, I get a product rule. So I get the derivative of the f times u plus f times the derivative of that u. Does that make sense? Now, what if I have two vector valued functions, u and v, and I left some space in the middle? This is undefined, right? We have to talk about, if you multiply two vectors together, you're either doing a dot product or a cross product, right? And so the formula here is if you have a dot product, the same product rule happens, you just use the dot product instead, right? So it's
Get visual.
u prime dotted with v plus u dotted with v prime. Does that make sense? I'm trying to think if I care about, I guess it's all laid out. And then you have a cross product one too. Let me just do it this way. Class. Okay, so dot or cross product can slide in there. You just do the same thing. All right. Oh, and then you also have the chain rule in the same way. So if you have the derivative of some vector valued function, but you plug some other function into that guy, that's the same thing as if you take the derivative of u and then you kick out the f prime at the end. So your chain rule works exactly the same way as it did back for ordinary functions. Okay. All right, so let's prove a theorem here. That u and let me just be clear. Okay, so here's the setup. You have a vector valued function u that's differentiable. Okay, so it just means the derivative exists everywhere. It's nice and well behaved, continuous actually. So you have a differentiable u where the size of u is constant. Okay, so well, yeah, I'll just say this. So think about the unit tangent vector, right? That was. We said you have this vector, a unit tangent vector is always of length 1, but it might move around along your function, right? Along your curve. But it always has a length 1. So this is where we're going to apply this thing here, this theorem. So the result is, for all t. So if this is true, then I guess I'll just say, then u is orthogonal to u prime. And so we'll see this. This will be very important in the next section. When we get to curvature. And you might be maybe just in parentheses here, because this is actually what we'll prove. How did you show two vectors were perpendicular or orthogonal to each other? You showed that something was 0. What was it?
U, vector U, dot product.
Right, so remember being perpendicular was equivalent to their dot product being 0. So if I want to show that u and u prime are orthogonal, I just really want to show that u of t dotted with u prime of t is 0. Does that make sense? So that's what we'll end up proving here. Okay, so one of the few things we'll actually prove, let's take a second and do this. So proof. Let u of t be differentiable with the magnitude of u a constant. All right, and so I'm going to use, I guess, I'm going to use the formula for the product rule of the dot product here in a second. But notice, if the magnitude of u is c, then what is u dot u?
It's 0
No.
or b.
No. What did the, not square root.
Oh,
We said this like 2 days ago.
Yeah, so the dot product of u with u was the magnitude of u squared. So it should be c squared. Does that make sense? So maybe I'll just write it out. It's the magnitude of u squared, so it's c squared. Point is, that's a constant too, right? So I have a constant number, I have a constant here. So now differentiate. And I'll just take my time. I have the derivative of u dot u, and that should be the derivative of c squared. Again, c squared is a constant, so what's the derivative of c squared? 0. Apply your rule over here for the dot product, right? That the derivative of u dot v is u prime dot v plus u dot v prime. In this case, that's u prime dot u, right? Plus u dot u prime. Does that make sense? Dot product is commutative though, right? So u prime dot u and u dot u prime are exactly the same thing, so you end up with 2 of these guys. Equals 0, divide by 2. So you get u dot u prime is 0, which implies u and u prime are orthogonal. Does that make sense? Again, this is another thing, don't get bogged down in the details of the proof, but we're going to use this fact in the next section, basically to show that the stuff we define makes sense. So last, thing for this section. Integration, so we're going to do more with integration later on. But I'll just say, right, if you have the integral of f g h dt, you just get the integral of f dt, integral of g, dt, integral of h dt, and then plus some constant vector. I suppose you could have just included your integrals in here, but we'll just do this with examples. And so you can do this for definite or indefinite integrals. I'd say for right now, the more interesting case is the indefinite integrals. If you think about, a vector valued function giving you the position of some particle, all the stuff you're used to back in calculus is going to hold. So if a function gave you position, then what was the derivative of the function? What did that represent?
Slope.
Well, it represents the slope for an arbitrary function. But if your function is giving you the position of something moving along a straight line, then the derivative was the velocity, right? Remember that? And the acceleration was the second derivative, right? And so if you have position being represented by a vector valued function, the same thing holds. Your derivative is velocity, your second derivative is acceleration. Now they're vectors, right? Not just numbers. And so you'll use this a lot there, right? If you can measure the velocity of a particle moving through space, then you can integrate it to get its position function. Right? You know how you measure the velocity, then you can backtrack to get position, and so on. So we'll use it for that. I think it's a couple sections from now before we get to a lot of motion in space. So right now we're just going to do this generically. So example, find the integral of well, let's just make an easy one. T squared plus 3t I plus 4 minus t j. So there's a vector valued function again. Just get two dimensions, easy enough to tweak over to 3 dimensions. Let's just do 2 examples. All right, so all you do is integrate each term, right? So there's nothing tricky. It's what?
2 squared,
Two-
or
T
2t.
T cubed, we're integrating. Right?
Oh, okay, yeah, no, you're right.
T cubed over 3, right? And then, is that okay?
Yeah.
Integrate, and then integrate 4t minus another t squared over 2, right? And then you could have added plus c1 here, right, and plus c2 here. They're different constants though, and so we usually just say plus some constant vector at the end. Does that make sense? Okay, let's try one more here. Let's see. So, I guess I'm going to make slightly different directions here. Find, it's essentially the same type of problem, but find the vector r, the vector valued function r, if r prime is 1 over t squared, comma, negative 1 over t, and r of 1 is the 0 vector. So if r prime, if we're given r prime, r is just the integral of r prime. And so if that's our r prime, what's the integral of 1 over t squared? Negative 1 over t. And if you need to, just think it's t to the negative 2, right? So add 1 to that power. Divide that through power. What's the integral of negative 1 over t?
Negative log t.
Negative nat log of absolute value of t, right? Won't matter here, but be careful. And then finally, integral of t.
T squared over 2.
Square over 2, good. And then you tack on a constant, right? And so then this should feel back like the initial value problems from Calc 1 or Calc 2. Now you plug in r of 1, right? Should be 0, so we have the 0 vector should be r of 1. What's r of 1 here? Negative 1. Log of 1 is 0. And then 1/2, right? Plus c, so our c is just 1, 0, negative 1/2, right? Let's move it to the other side. And so we end up then with our final, okay, I'll just write it. So C is 1, 0, -1/2, and so our final formula for R is the vector we came up with plus that C, right? So it'll be -1/t plus 1.
Should -1.
No, we're moving it to the other side, right? So plus 1 and then negative log of absolute value of t plus 0 and t squared. That makes sense? So try the homework from this section, see if you encounter any problems, but for the most part, we're really gonna do more with the integral when we get to the section on positions in space or motion in space. So, all right, so we'll stop there.